Okay, so now we move to the second part of the chapter 3, where this is about the triple integral. Okay, so now let's say we have a quick revision on double integral. So for double integral, you have two curly things here. So your integral is a function in terms of two variables, x, y. Okay, and you have the over the region. Alright. So for double integral, we considered two different coordinate system where we only have the Cartesian coordinate, or we call that as a rectangular coordinate system, Cartesian or rectangular coordinate system, where your variable containing the x, y, okay, x, y. Okay, but sometimes if you have the region is part of the circle, so it's much easier for you to solve that in polar. Okay, polar coordinate system, where your variables now is in terms of r and theta. Okay, so what we have done in double integral, you have looked at the application where you can obtain the area of region, and also you can evaluate the volume of solid. Okay, area of region. Okay, and then we also have discussed on how can we evaluate the mass of the lamina. Where lamina is considered as just like a curve on 2D. Okay, mass, and you have the moment of mass, capital M, and we also have learned how to evaluate the second moment, which is the moment of inertia. So that is the thing that we have learned, you have done in double integral. Okay, but now we want to continue our understanding on double integral, where now we want to put another curly things here. We want to add another one, so we call that as triple integral. So for triple integral, you still have the Cartesian, you still have something like polar, but we call that as a cylindrical coordinate. Okay, but the basic is coming from the polar. Okay, but then because now you have a triple integral, so now you have triple integral, so your density function can be in terms of x, y, and z. Okay, and if double integral, we call that as dA. Now we have dV. Okay, so if this one, if double integral only for region, so you have R. So for triple integral, we have something about solid, where in general we put G. Okay, so we have a solid G. Why G? Just a name. Okay, just to tell you, R is for region, which is on 2D, and G is a solid for 3D. Okay, but for double integral, you have to have R, but for triple integral, you have to have G. Okay, but just like the double integral, you have to know how to determine the the order of integration, and from the order of integration that you choose, that you decided to have, then you can determine your limit. So the similar process for triple integral. Okay, so I will show you how can we evaluate the triple integral in Cartesian, in just like polar, and we have another one where we call it as a spherical coordinate. It's just a quick introduction. So we have the Cartesian coordinate system. We have just like polar, but we call that a cylindrical coordinate system. And the third one, we have spherical. Okay, so as you can see here, the word here, cylindrical, is coming from the word cylinder. So the base is just like a cylinder. And spherical, the base is sphere, because the the basic idea of the spherical coordinate is coming from the sphere, the solid where it is like a sphere. Okay, but now what is the application that we want to have? About the application, we want to know how can we evaluate using triple integral to obtain the volume. Yeah, it is the same volume here. But the top one here, you want to evaluate the volume using double integral. And for this one, you compute the same volume using triple integral. Okay, and what else? We can use triple integral to evaluate the yeah, I will explain in detail later on. Okay, so that is about the triple integral. So what is our objective in this part? You have to sketch, you have to know how to sketch a solid, that is must, where it is the continuation from the chapter 1, right? So we want to evaluate the triple integral for Cartesian, cylindrical and spherical, as I mentioned here. And the third one, it is about the application. So we can use the triple integral to evaluate the volume. And similar for the previous video, we use the double integral to evaluate the mass of the lumina. But now you want to evaluate the mass of solid, the center of mass of solid, and the second moment of the solid. Okay, so this just outline. This is a general definition, but we don't want to focus on this. So okay, so about the how can we choose the order of integration. Okay, so the order of integration. So this one is actually the continuation from the application. Did you remember that last time I already explained to you how can we use the double integral to evaluate the volume of a solid, right? Okay, but then I didn't want to repeat this, so I just want to focus here. Okay, but actually the idea is the same as you want to solve or you want to compute the volume using double integral. Okay, but we just I just want to focus for this part, which is triple integral. Okay, so now in terms of okay, I don't want to explain this one okay, so I don't want to focus on this slide first, because this is just the sentence, the instruction that you can see maybe in some books and maybe in the past final exam or past tests. Okay, maybe we will look at this after we done everything in this chapter. Okay, so now we start with the if we have a double integral. So now I want to relate with double integral. So double integral, so let's say you have a general integral dA. So now your region is a rectangular region. So let's say you have 0, A, this one is C. Okay, so all your limit are constant. Remember that if we have a rectangular region, if you have a rectangle, so the limit of x and the limit of y is constant, and we call it as a rectangular region. Similarly for solid, okay, now we are talking about triple integral. So if all your limits are constant, which means that you have a cuboid. Okay, so let's say based on this one, so you have the, I try to draw in 3D. So what is the shape that you can have? So this is x, and this is y, and this is z. So now x is from A to B. Okay, A to B, A, B. Okay, and that is the line. And then y is C to D. So this is C, and this is D. So I draw a line. So you can see that on xy plane, you can see a rectangular region. Okay, now you look at the z. Z is K to L. K, L. So if you do the projection, so I do the projection. So that is the, maybe I should change the color. This one, this one, this one, and this one. Okay, so we have a cuboid in surface where you can touch that. Okay, so we have a rectangular solid, which means that when all your limits for x, y, z, they are all constant, so we have a rectangular solid. Okay, not rectangular region. Rectangular region is for 2D, just this one. So this is called region, which is rectangle. And but this one, when you do projection, you have a rectangular solid. Okay, now in terms of the order of integration. So for dA last time, we have only two options, whether if your region on xy, so you have dx dy, sorry, you have a dx dy or dy dx, only two options if your region is on xy. Okay, but then if you look at here, for triple integral, you can have 6 options. 1, 2, 3, 4, 5, 6. So you have to choose one about 6 where it is to be your order of integration. For 2 is okay, because whether this one, whether this or this, but this one, it is something complicated. I mean, not complicated, but you need to decide. You have an extra time to decide what is the most appropriate order of integration that suit with your triple integral that you want to solve. Okay, it looks, but don't worry, it is not so complicated. There's a way for you to determine which is the most appropriate one. But you have to follow the step. You cannot just mix up. So if you mix up the process, then it's just gone, just lost. You cannot get the correct order of integration. Okay, so I will explain to you later how can we decide. But firstly, I want to just for the quick introduction, I mean the quick just starting about the triple integral. We just evaluate the integration of this, this triple integral over the rectangular box or cuboid, where you can see that all the limits are constant. But just to highlight here, there is no such question in the exam. Just the first started. Okay, just like you to start the engine about this triple integral. Okay, so how can we solve or we compute the triple integral if we have the function? So your function here is a 3-variable function. Okay, it can be just x, can be just y, it can be just z, or the combination of just 2 of them or all of them, x, y, z. Okay, so let's say in this case we have the 3 of them. We have the z, which is x squared, and we have a y, and we have the x. So x squared, y dx. So they give you the dv. Okay, for double integral we have dA, A for area, V is for volume. Okay, okay, I will explain to you why we have volume here. But then we just want to focus on computing the triple integral if you are given the limit and all the limits are constant. So now we have to decide. We have a 6 option, right? We have a 6 option, then which is which? Okay, now because of all your limits are constant, so we should have no problem. you can just start with x first, and then y, and then z. So let's say I follow the provided in the notes here, where we have, so the order is dx, dy, dz, which means that you have to integrate respect to x first, and then y, and then z. Okay, but if you want to choose a different, let's say you have y at z, then you have to integrate respect to y, and then after the x, and after that z. Okay, but in this case we have no problem because the limits are for the x, y, z are constant and they are all given. So we just copy the given interval. So x is the inner one, so the first integration, so 0 to 1, x and y now is 1 to 2, and z is -1 to 1. So now, just like the double integral, so you want to integrate with respect to x, so we just, in this case z squared y is constant, so z squared y is constant, and we just integrate ex with respect to x. So we have integration, we just have ex, and then we replace x from 0 to 1. Okay, and then now we substitute, so we have z squared y e1 minus e0 e1 z. So we have e1 is constant, e0 is 1, so e1 minus 1. I just put it outside because it is constant. So now we only have z squared y dy dz. So next we integrate respect to y. So z here is constant. So e1 minus 1. Now integrate respect to y. So z squared constant at y squared over 2. And limit of y is 1 to 2. Y is from 1, y to 2. dz. So again, when you substitute, you will get, so z squared 4 over 2 minus 1 over 2. So again, this one will give you a constant, so I can just take it out. So we will get 3 over 2. So 3 over 2 z squared dz. So now 3 over 2 p minus 1. So z cubed over 3. So z is from between 1 to 1. So 3 over 2 p minus 1. So 1 over 3 plus 1 over 3. So 3 over 2, 2 over 3 p minus 1. So I can see out, and we will get this one. Okay, just a practice to deal with a triple integration, how you can compute. But this one is I think not, yeah, you need to, especially when you have something complicated form to be integrated. But if this have a polynomial, it should be no problem, but it's quite tedious. I mean, tedious in terms of you have a polynomial, there are so many terms. But here in this case, it's not only the calculation of integration itself, but the way how can you provide the order. You have to decide which order to use, and what is the limit that should be that we should have. So that is another problem that we will face when we want to solve the triple integral. Okay, but if you follow the step, so it should be okay. Okay, so for here for rectangular solid, it is not so complicated, but meaning that if you want to swap you want to change the order, so you just change the particular interval, and then you just do the integration one by one. But now the problem, if we have the non-rectangular solid, okay, where your function, your limit should be function only the outer. Okay, remember, for double integral or for double integral or for triple integral, so the outer integral should be all constant. So because of we want to make sure our final solution is a number, because we go to the basic of the finite integral, where the integration there are limits, so the final solution should be a constant. So to make sure that we have a number, we have a value of that double or triple integral, we have to make sure that our outer integral here, the limit of them should be all constant. Okay, so in order for guiding us which order of integration is possible, because remember we have 6 options, okay, 6 options, but you only need to use just one of them. So then to guide you to get an appropriate order of integration, we try to sort the solid that you have into type. Okay, type 1, type 2, type 3. But don't worry, in the exam we don't ask you to just to give a name for that particular solid. It's just to guide you to choose a correct order of integration. Okay, so if you have the solid, then you have to decide what kind of solid that you have, whether it is XY solid, or you have XZ solid, or YZ solid. Okay, how can you decide? How can you decide if you have that particular solid? We have already sketched that for some particular orientation. So how can I give a name for that solid? What is the thing that I refer to so that I can give a name? So remember, I explained to you last time about finding the volume for double integral. So I'm not sure whether the sketching is still here or not. Finding the volume. Okay, remember, let's say this one, I'm not sure on which example, but if you refer to my previous your previous notes, you have this sketching. So I ask you to determine I ask you to sketch a small people here, and you have to decide which is to be your region. So in Malay I would say, kat mana you pijak? Okay, region you tu kat mana? Kaki you tu kat mana? Apa yang you pijak? Okay, what I'm saying here is you have to look at your own sketching, and then you have to decide where is your feet now. Okay, your feet here on XY plane, or on XZ plane, or ZY plane. So in this case, your region, your feet here is on XY. So for this particular solid, we give the name of this solid is called XY solid. So what is XY? XY is referring to your region. Where is your region? Okay, how can I have a region? Region means the plane that your feet is lying on. You pijak dekat mana? Okay, now you can see that your feet here is on the XY. So we give a name, we have a XY solid. Okay, so let's say you have a different sketching, you have a different solid, but your feet, right? So let's say you have maybe a bowl concave down. Okay, your solid is a bowl concave down, but this one is not Z. This one, let's say Y, and this one is X, and this one is Z. So which means that your equation of your bowl is actually Y equal to let's say 4 minus x squared minus z squared. So this is 4. So now they ask you to evaluate the volume of this particular solid. So your solid is bounded by the ball concave down and the x equal to 0 plane. So this is x0 plane. So this is not x but y equal to 0, and this one is 4 minus, so y equal to 4 minus x squared minus z squared. So now for you to find the volume using double integral, remember I asked you to put the r here and then give a name, whether x, y, and z or whatever. But then in this case, if you sketch the small people, so now look at where is the feet of the feet of the small people. So it is lying on exact plane. So you put the exact. So now you know that your region is lying on exact plane. So if I want to give a name for this particular solid, so this is called exact solid, where your region is on exact plane. So that is the way how can you give a name for the solid that you have. Okay, so if you have xy solid, meaning that your region here is on xy plane. But if you have exact solid, so your region is lying on exact plane. If you have yz solid, so your region is lying on yz plane. Okay. So then after you decided, after you give a name for the solid that we have, then we can proceed to determine the order of integration and so on. Okay, but I don't want to explain this one. I will explain to you from the example that I have here. Okay, so in this example, we are given a solid. Okay, remember I have told you before, this one is G. Because R, capital R, we know that that is specifically for the region, which is something onto G. But G, we have a G here specifically for solid integrity. Okay, so the solid that we have is the wedge. So wedge is a non-rectangular solid. Okay, so the shape of this wedge is depend on what is the instruction that provided here. So the wedge is lying on the first octant. Okay, what can you understand with the word first octant? First octant means the x, the y, and the z are all positive. Okay, because remember that I think last time I already told you that octant is actually 8, right? We have 8 parts in 3D system. So for 8, this is 3D. So this is x positive, this is y positive, and this is z positive. So if they stated that there is a first octant, meaning that your sketching, your solid, your graph should be lying on the x positive, lying on the positive, y positive, and x positive. So it should be in this region. I don't know how to this area. Okay, this one, this one, something. Your surface, your graph should be only this area. Okay, they are all positive. And okay, again, your solid is lying on the first octant, which is from the cylindrical. So you have to sketch them. That is the hardest part. That is the I think the student cannot do this very well. This triple integral or double integral very well because of they have problem on sketching in 3D. So because of when you cannot sketch the solid correctly, so you cannot determine the limit and you cannot determine the order of integration. So then because of you cannot provide all the very critical parts in the triple or double integral, then you cannot evaluate them. So that's why I told you, please do exercises on sketching again and again, and please spend some time to do the revision yourself. Okay. Okay, so now in order for us to know exactly what is the wedge, what is the solid that we have, then you have to sketch the surface. The surface is how many surfaces that we have here. We have the y squared plus z equal to 1 surface. This is a cylinder, and you have the plane. So you've got 3 surfaces here. Okay, so the first one is y squared plus z squared equal to 1. So we know that I don't want to explain the traces or whatsoever, the projection, so please do it yourself. This is on the chapter 1. Okay, but in this case, I want to have y here and z here, and this one is supposed to be x. So originally we have a cylinder. Okay, and then that cylinder is lying along the x-axis. So we have the circle with radius 1, and we do the projection, and we got a cylinder. This cylinder lying along the x-axis. Okay, but then because of we want the graph should be only the x positive, the z positive, and the y positive, so the correct one is actually just a quarter of the circle on the yz plane, and then when we do the projection, we have this one. So that is the cylinder that we have. So this is 1, this is 1. So this is actually open cylinder. Just part of the surface of the cylinder of y squared plus z squared equal to 1. This is still open, but this is still not a solid. What is actually the solid? Solid is the closed and bounded surface. This is still open. So how can you make it close? So to make it close, so you have to have the plane x equal to 0. So where is x equal to 0? So if this is x, so x0 should be the floor down here. Okay, but now because of we want to have on the first quadrant, sorry, first octant, so this is the surface of x equal to 0. So we close that, we close our surface down here, but there's something at the back here still open, right? But because of there is a word, okay, y equal to, okay, we have a y equal to x. So the line of y equal to x. So what is the, so firstly, of course we don't have any idea, so we have to sketch the plane y equal to x. So y equal to x, when we do the trace, so y on y-x plane we have a line, but because of we only focus on y positive, x positive, so our line is just this one. And after that we do the projection. So when we do the projection, so this is a new y and this is a new x, so then we have a similar line. Okay, so your plane is actually this one. So that is the plane of y equal to x. Okay, so and this one, the way is on the first octant, so it is understood that we can close the plane at the back here. It is closed, and the plane on the side wall here also closed. Right, so now we can see that down here is closed, and the plane back here it is y equal to 0, it is closed, and z equal to 0, here it is closed. But the top here, this one, what color that I have to use? So this still open, so how can you make it close? So we can say that we can close it by using this plane. But what is actually the shape looks like? So in order for you to combine all the surfaces together on the same 3D system, you have to make sure you have a similar orientation. So if you have this one, so it looks like you don't have a similar orientation, right? So this is for Z. So this is Z. You have Y, X, Z, but this one is X, Z, Y. So maybe this one you have to change this. So it is up to you. You have to decide yourself. So for me, I will refer to this orientation. So which means that I want to have X here and Z here and Y here. So I have to redraw the plane using this orientation. So I want to have X here. So this is Y and this is Z. Okay, so if I change the orientation, so now the plane is in this form. Actually, we have the same plane here but different orientation. So now we join this plane to this part of cylinder. So now you have exact. So looks like when you cut it, so you can see the line here, right, on the y-axis. So you have this line, should refer to this line. So I sketch this blue line over here. That is the blue line. And then you can see the line here, right? But because of the length of this plane infinitely very long, but then it's referred to the Z here is just at X equal to 1. So we can assume this one to be 1. Okay, so that is the line. And then because imagine you have this solid and you cut, you have a knife. So imagine you have a cake, part of the cake. Okay, part of the cake. Your cake is a Swiss roll cake, and you just cut into a quarter of the cake, and you take a knife, and your knife is in this form, and you cut it. So maybe something like that. Okay, so that is part of the blue here is part of this plane. Okay, I cannot use the red as well because there is a red color as well here. So I will say that now the cylinder here is cut by this plane. So this is the plane in blue. So now what is actually your the solid left after you cut the cylinder by this plane, blue plane, the blue plane. So you will have something like, so you still have this one, you still have this one, which is this is at Y, and this is at Z, and this at X, and this one. So because this one is in 3D, it's facing backward, okay, backward. So something like, maybe this one is at the back, you can't see that. So this is part of the plane. So this one, after you cut your cylinder by this plane, which is this one, now this is the result that you obtain. Okay, so maybe my sketching is not so correct, but the important here, I don't penalize you if you sketch not so correct, but as long as you can provide me which will be your lower bound and the upper bound, that is okay. And also because sometimes there is a mark for you to, if you obtain to me, if you sketch the solid to me, sometimes there is a mark, but sometimes there is no mark. But the mark is just maybe 1, okay, and maybe 2, but normally it's just 1, just to help you to determine the limit of the X, Y, or Z. Okay, but sometimes you can imagine that, you can imagine your solid in your mind, but it's quite complicated for you to transform your imagination on the paper. But I will look at on your traces and whatsoever. So if your traces, it looks okay, looks correct, it looks make sense, then I can give you mark. even though your sketching is not exactly as in the answer scheme. You understand that? As long as you can tell me what is the correct lower bound and upper bound for x, y, and z. Okay, so now that is the solid for this particular example. Okay, but if you look at the solid provided here, it is a different. Because why? Because we have a different orientation. Okay, we have a different orientation. So for this particular orientation, you have z here, you have x, and you have y. So you can see that if this is your region, sorry, this is your solid. Okay, so now now because you want to evaluate, okay, what is the instruction here? You have to evaluate this triple integral. So you have to determine your dv, right? So now we just discuss on how can we determine the dv. So first you have to, what is the first step? So first step, you have to give a name, whether your solid is xy solid, xz solid, or yz solid. Okay, so now if your solid is like this, so you just sketch. After you sketch your solid, please always sketch the small people inside. Okay, so the small people in the standard orientation, the standard how you standing up in the as a normal people. So you will stand up like this, right? So where your feet is lying on this plane. So what is the plane here? So you have xy plane. So if you have this particular solid for this particular orientation, so your solid here is called xy solid, where your solid is lying, your region is lying on xy plane. But if you have this kind of solid, so next you sketch that small people. You sketch the small people. So where is your feet lying on? Kat mana kaki awak berpijak? So where is your feet lying on? So your feet is lying on so on this plane, right? So that plane belongs to yz. So if you have this kind of orientation and with this particular people where it is standing on the yz plane, so we can say that this solid is called zy solid, or zy or yz solid. Okay, where your region is on yz plane. Okay, so now the second step. So now we decided to have this particular region on yz plane. So in terms of your dv now, so your dv is actually the, okay, so I want to relate with the dA. You have double integral and the function and dA. So dA here is area of the region. Okay, so if you have volume, so how can you have volume? So something, the height multiplied by the area, right? So meaning that here part of your dv will be, you will have the dA, where the dA multiplied by the height and you will get the volume. Remember, dA here is area. Area multiplied by the height will give you the volume. So in this case, if you relate with the double integral, your dA here related to the region, right? So in this case, your area is dA, you have to look at from your region. Remember, how can you determine the order of integration for dA? You have to look at the region. Okay, you have to decide which one to be constant, which one to be function. So the similar way here. So if you said just now your region here, so if you have this name, meaning that your region is lying on yz, so you have to put your dA on yz. So you know that part of the dA here should be dy dz or dz dy. Now what is the thing that you have to put here? What d? Is it dy? You have dy already here. Is it dz? No, it is already inside the dA. But what else? What is the variable that you can't see? You cannot see here. X, right? then you have to put the dx. Okay, so from here you can have two options. So you have dx till dx. Sorry, so maybe I got maybe. So from here you can have two options. So the first option is just dx, and then look at your dA here, dy, dz. Or you can have a second option where you still have dx does not change, but you just change the dA, which is now you have dz, dy. So from 4, 5, 6 options that you have to look, now it just reduced into 2. The process is the same as double integral, just 2. Okay, so now how can we have this? Because you have to refer your solid, the type of your solid. Again, how can you determine that? Look at your sketching. If you have this particular orientation, so this is your sketching of your solid. So now ask yourself, where is my feet lying on? Your feet is lying on YZ plane. So you just put the YZ solid, meaning that your region is lying on YZ. So you just put for this particular kind of type of solid, our region should be lying on YZ plane. And because of that, in order for you to determine the dV, so as we know that part of the dV, there is a dA. Okay, and because of dA is referring to the region, so now look at your region here. Your region should be on YZ, so you put the YZ just to let you know that inside the dA should be dy dz or dz dy. So but how about this one? How this one should be something not related to, I mean, if you have a dy and z, this one should be x. Okay, so now you have dx, dy dz, or dx, dz, dy. So now from 6 options, it reduced to only 2 options. Okay, so now, so to determine, now from 6 you have only 2. So now you have to choose whether dy dz or dz dy. So you have to look at your region. Okay, so for triple integral, the last 2 order, you have to look at your region. So now your region is lying on YZ plane. So what is the sketching of your region on YZ plane or ZY plane? It is part of circle, right? Circle with radius 2, which is coming from your trace to obtain your cylinder, this one. So it is part of the radius with radius 1. So that is your region, where it's coming from the formula of, it should be mentioned here, the formula of this one. Okay, so this one is part of the y square plus z square equal to 1. Okay, so now okay, based on our region here, so you have to decide because now based on our dV just now, you want to have x constant or y constant. Okay, so here I want to stress out that you got the triple integral, right? So the last 2 integration here, which is your dA, you have to just look at the region. Okay, so now for dy dz or dz dy, you just look at your region on zy plane. And now let's say we decided to have the z constant. Okay, so when z constant, so we have to choose the line that we have to choose to guide us to determine the limit should be horizontal. Okay, so you can see that the z is, sorry, I should use this one. So z constant should be 0 to 1, right? Okay, clearly see. So z is 0 to 1. And then based on this line. So this is your lower bound of y and this is your upper bound of y. So y should be from 0 to, and the upper bound is part of the circle. So you have to rearrange this equation. So your equation here should be y. So y squared is 1 minus z squared. And we only interested on the positive value of y. So we just take the positive square root. Because we know that this region is lying on the z positive and y positive. So that's why we consider only positive square root of 1 minus z squared. So we can see that now your upper bound of y is positive square root of 1 minus z squared. Okay, so now we already obtained the limit of, okay, d, we have z constant, so dy dz, z is from 0 to 1, and y is from 0 to square root, positive square root of 1 minus z squared. How about limit of x? We don't have this limit yet, right? So for that, for the first integration here, you have to look at your solid. Okay, now look at your solid. Now ask yourself, who will be your lower bound if this is you. Imagine this is you, and who is your lower bound and who is covering you up here. So you can see that based on the information provided here, so because it is stated that your lower bound is at x equal to 0. This one is close by the x equal to 0, so we know that our floor is x equal to 0. So then we can write down the lower bound is 0, and then who is covering you here? So the surface that covering you here is part of the plane of y equal to x. But we don't read y equal to, but we read for x equal to. So x equal to y. So now we already obtained the limit of x is 0 to y. So we just substitute here. So the limit of x is 0 to y. And then you can evaluate that. So when you evaluate that, for this, I don't want to solve step by step. So I'm sure that you can do it. It's not so complicated, and you will obtain that the result of this, the triple integral of this using this order of integration is 1 over 8, where the answer should be the same as if you choose this kind of orientation, and this is your region looks like. You can see that your sketching is totally different because of we don't say that we have a different solid, we have a similar solid. It looks different because we have a different orientation. Okay. Okay, for practice, I want you to try to obtain this kind of solid using this orientation. So you will obtain that your region which is lying on y-axis plane is this particular triangle. So you will finally got the similar answer. So actually the thing that I provide you here is actually also provided here, but this is just part of the result, but they don't show you the solid for this orientation, which is this one.